Yeah, I hope I will finish. Welcome everybody to this idea seminar with our Danish Institute of Advanced Studies. And it's my pleasure to present today's speaker, Jonas Beerman, who is associate professor and working on nano-optics in our Center for Nano-Optics. And I can tell you that I have been known Jonas basically from the time that he was a student at Aalborg University, but we really started interacting when he came to me as a PhD student. I think it was around 2000 in Aalborg University. And since then he has been working with different topics within plasmonics. So plasmonics, that is something where we learn how light is interacting with metal nanostructures. So probably you may heard something about it, but the point is that when the light is interacting with metals, then well, you know metals are shiny, but they can really change the properties of light and create strong fields and so on and so forth. So this subject of abilities of enhancing the fields, optical fields, by means of surface metal nanostructures, that is the central subject in the research of Jonas Beerman. And during these years he has been involved in different directions, different projects. We participated in European projects, we in several Danish projects looking for the possibilities of using these nanostructures for sensing applications, and I guess part of it would be presented today, but we also looked a bit about the usage of plasmonic nanostructures for medicine or biology. We have even managed to publish a paper in cancer research letters. Cancer research letters. It's not so easy to publish if you are doing pure physics. But that was about identification of cancer cells under when they're still embryonic cells, non-differentiated, and so on and so forth. So there are many aspects of it, and I should also mention that Jonas is quite successfully doing research, reaching to published more than 50 papers and reached quite a high level of Hirsch index 18. That's quite a good achievement, taking into account the career span and the necessity to teach, which we know, well, it's something we have to do being at the university, but not always very helpful when you're doing research. So I'm sure Jonas will present a more detailed description of what is within his current interest, and yeah, I will leave you the word now.
Okay. Thank you very much, Sergey. And yes, and it's nice to already have a little bit of introduction to this topic. So the topic is really, it's about metal structures, and I put a question mark to try to make it a little bit more broad interest. And so the application can be sensor, so sensor applications, and it's in metal structures. So the outline first, I will just very briefly mention what is this enhancement of the electric field in a metal structure. This is what we can use if we want to make a sensor, which is very efficient. And so this is kind of the purpose is to make an efficient sensor. But then we have some tools, and one tool which I used for a long time now, this is this microscopy, nonlinear microscopy, where it's called two-photon luminescence. We absorb two photons at the same time, and then we use that to map this enhancement in the nanostructure. And the text book example is this structure, which is not a simple structure, but it's really like a really good example showing how efficient this technique is. But then I will move to the simple structure, and this is some very thin films, of gold, where we have a really large enhancement. And then we saw some additional nice, very interesting details, which also have some nice applications. So that's the idea. So just very briefly, so why metals? And this is because of the charge electrons in the metals. We can get them to oscillate along with the light. So the light is an electric field, and when it interacts with the electrons in the metal, you can get either a propagating wave of these electrons along this metal and air interface. So you can get a propagation of this wave in the electrons, or you can get it localized to a single metal particle. Then you can also have, you can imagine a standing wave. So if the wavelength fits to the size of the particle, you can have a resonance, and then you can have an enhanced field. So this is really this can be a little bit technical, but the purpose is to get as high field enhancements as possible, and then use this as a sensor. So it was done before, so I think many of you saw this picture before, but actually small particles, they have a color, and this is because of this resonance. Depending on the surrounding material, that could be glass, then it could be a gold particle here, then it will have a resonance. They will have a certain color here, and you can change the surroundings. Then you actually can move a little bit the resonance, use it as a sensor. It's quite old actually, but we want really to have a significant field enhancement, and maybe we could design really specially a structure like that. But that would be really difficult, and it would take a long time. We need a very expensive equipment. We have this here at STU, but we really need expensive equipment, and it's difficult. So it would be nice to have a simple structure. And that's the idea. Maybe we could make just have some random distributed scatterers here, and then some position in this scatters. There would be an increased electric field. So the idea is we have all these small particles, and each of them can be in resonance with this light that we send in. So if they have a certain color, they can be in resonance with that color. And then when we put some molecule here, it feels not only the light that we send in on this molecule. This light can be used to to get a signal from what molecule. Is it some poison? Is it an acid, or what kind of atoms do we have in this molecule? What kind of bonds do we have? And then we put it near to the surface, and then if the surface itself enhances this incident light, we have increased signal. And then we get a fingerprint of this molecule. And this is called Raman scattering. And if it's enhanced at the surface, then it's surface enhanced Raman scattering. So that's really the purpose of the research, one branch of the research, to find the ideal structure, to find a cheap, fast, easy to fabricate structure, and then it should be efficient at the same time. Then we want to know how do we estimate this enhancement, and there is the technique. We use a pulsed laser, very short pulses, femtoseconds, 10 to the minus 15 seconds, 100 of those, very short pulses. And then we focus it, and it means we get really high peak intensity. The moment this hits, we have really significant intensity, and we focus it at the same time. And then there is a certain probability that two photons in this light will be absorbed at the same time. And that will really, since we have two photons at the same time, it's a square dependence on the incident power. So if we double the intensity, we have 4 times more photons here. And it means if the sample locally enhances the electric field, then we kind of square that dependence. So we see it much more clearly in our measurement. And this is the than the textbook example of this. If we have a channel which is really narrow and ends here, then we send in light with some electric field here. When it reaches the bottom, we have increased electric field. And then we have increased photoluminescence from the bottom. So here it was made really nice grooves. When we shine just normal light on that from the top, it looks dark because the light is trapped in these grooves. And it's important that the electric field of the incident light, it's a wave, so it oscillates. If you can bring it to oscillate here along this direction, I mean perpendicular to the groove, it will be absorbed in the groove. There will be a resonance, and this wave will be absorbed. And then if you turn it, then the other one will be dark. So it really depends on the polarization of the light, the way the electric field is oriented. And we will use that during the presentation. So if I look at the two-photon luminescence, here it's just a normal reflection, it looks dark when I use this setup. So this here reflection just looks dark, depending on which polarization is sent in and which polarization I detect. But in the two-photon luminescence, it lights up because only for this direction light can enter the groove, and only there we have enhancement. So this lights up. Here it's a little bit brighter because it's a little bit more open. So then light can easier get up again and out and be detected here. So if we look at the center, the cross where the grooves were crossing, we can actually enter with this, and we can also detect the other one because it can escape for both directions. So this bright spot really shows that it's polarized. This emission is actually polarized, and it's coming from the bottom of the groove. And here, if we have a groove here, again we can excite it. It looks dark here with this polarization. We can get enhancement from the bottom of the groove for the correct polarization. But if we want to detect, instead of this one, detect the other polarization, then the light cannot enter with this polarization, and it can also not exit. So it can enter because we excite here, it can only exit with this. So we don't see any signal from the bottom of the groove. We only see from these defects here. So it's really sensitive to defects along the groove. So that's why the technique is so nice. You can really see small fine details. So, as you probably guessed, this is not a simple structure to make. It's made with, you take ions and focus the ions, and you bombard the gold film here, and then you remove away some gold atoms, and you mill some grooves in gold. It's really not easy. But something a little bit more easy is to make thin films of gold, just evaporate gold and make those films. So we can send in electrons and get the gold to evaporate, and then it will evaporate and reach a piece of glass. Then you have a thin gold film here. So it's 3 nanometer thick, and 3 nanometer, I hope you know, but it's really like, it's around a million of a millimeter. So it's 10 to the minus 9 is nano. And we have 3, 6, 8, 10, and 12. And somewhere you can see we have a lot of nice grooves, a lot of nice gaps. So if you're looking for a large enhancement of this two-photon luminescence, or a large enhancement of the really local electric field here, then we are really happy because we get nearly for free, we get a lot of nice cracks and gaps in the structure. So we make this, we look at the reflection, and it's clear only 3 nanometer of gold is already gives this reflection. If we move to 12 nanometer, we already see larger reflection here. And we always do this kind of investigation before we look at enhancement. Because maybe if there's a strong resonance, we will see really a dip here. Here it just starts to resemble flat gold. So there's so many resonances in this structure because there's all kinds of different shapes. So we don't have any specific resonance, but we have a broad range of resonances. And the same, opposite with transmission, how much light goes through the sample. You also see already 12 nanometer gold, you can actually shine light through gold film. But it's only 12 nanometer thick gold film. It's nearly flat, nearly continuous gold film. And then we look, especially around 6 nanometer thickness, we start having something called the percolation threshold. And this is where it's just becoming connected. All these small isolated islands here, they start to grow together so that you can find a path through the structure where the current can run, where an electron can move. So just around here we know that there's a certain size of the gaps, and some gaps are closed, but there's still quite a significant number of gaps. And exactly here we found, when we used the two-photon luminescence, we found quite large signal. But remember, we shined with the laser, and the spot size of the laser is around nearly 1 micrometer, so nearly this size. So we illuminate quite large area. And the electric field, of course, oscillates with the optical frequency, but then depending on how the electrons move, and if there is a resonance, or if they find a place where they can move, and then they cannot move any longer, then there will be an electric field here between, and each particle will also have a strong resonance. So, but there will be many different places here. So the image here will not be that nice and detailed as this text example I showed before. So it will just be a blurred image. That's why it's so nice to show the really detailed before. Because this is just one big kind of average signal. These bright spots, they are coming, from inside this collection of hot spots. Each of these we call it a hot spot. Really a place of strong field enhancement. But the average here is more or less the same. It's not that much really bright spots. So usually we evaluate the enhancement just by looking at the signal and compare it to a flat gold film. This we don't want to go into detail now. But then we take the same structure. Well, maybe I should mention that when we did this, we got significant number. Quite significant overall enhancement, actually, from this structure. Then we took the structure and put some molecule here. It's crystal violet. It's this molecule. We put it on top of the structure, and then we use this Raman microscopy on this sample with a thin layer, not even layer, but a thin, low concentration of this molecule. And then we see the Raman spectrum of this molecule. It's like a fingerprint, that this is this type molecule. It has exactly this bond, and this bond. All these lines shows a fingerprint of the molecule. And we see that for 6 nanometer thickness of the gold, we have significant enhancement. The others are lower. So, and if we took just a flat gold, we will have nothing. So all these structures are actually quite good at enhancing the electric field. So this could be nearly the end of the talk, the simple structure. But we just got a lot of details actually. We found so the Raman image showing the intensity of this. But after looking at the structure here, we found really nice details. We turned out that if we look at the power dependence, so maybe remember that the two-photon luminescence should be a square power dependence, and that would be around here. And this is more or less for 12 nanometer. We have around the square power dependence. It actually turns out that we have a power dependence which is more close to 3.4. So something else is going on in the sample. It's not only two-photon luminescence. It could be this so-called white light generation, and it's really a signature of really extreme field enhancement. It was shown first time in the Science paper in 2005, so it's quite a long time ago, but that was the first paper looking for that. But it's really a signature of large enhancement. So of course we got interested in what is going on. So that's the next topic. This is this white light super continuum generation, and this is the Science paper, and we try to make our own spectrum. We more or less immediately, I don't know, but we quite fast got the spectrum actually, and because it turned out the signal is so large that you can see it with your eyes. It's really the sample is giving a significant emission, and we can look at the different power dependencies, different places on this curve. So it shows it's not everything is something is nearly square, something is around 3. So, but still, this is quite simple to make compared to this. With the previous paper, it was really designed nano antenna with a small gap, and they made many of those, and 1 or 2 of those had maybe 5 nanometer gap, really nice enhancement. Here we have just a lot of different gaps. So it's white light because it's nearly the entire visible spectrum here. And we of course did further investigations. We made another set of samples, again used two-photon luminescence. It's clear that if here we have the difference between a flat gold film and a gold film which is this very, very thin with a lot of roughness. And you see significant signal here, practically no signal from the flat gold. And the opposite in this, what we call fundamental harmonic, what this is the usual reflection here. Here's the opposite. A flat piece of gold shines a lot. It reflects nearly 100% at some wavelengths. Whereas the thin film, it has this absorption because of this scattering and all this in the structure. Then we made careful measurements of how well could the electrons propagate through the structure. We made thin stripes here, 1 millimeter long and around 1/4 millimeter wide, and then the thickness of the thin layers, and depending on how thick, you saw the resistance in pure gold. The resistance is nearly 0 here, right? But it starts up coming up to a maximum here around this percolation threshold, where it starts to be a lot of gaps between the gold structure. And at the same time we have the two-photon luminescence signal, so it has a maximum here. And it shows there's a big correlation between the gaps and how complete the gold structure is, and then the two-photon luminescence. And we have here more white light generation spectra on the different thicknesses. Exactly at 5, this is where we have this percolation threshold. This is where we have the largest white light generation. So it all makes sense. And then if we look at all this reflection spectrum, there's one nice detail actually, that the 5 nanometer, they follow more or less step by step here, but the 5 nanometer goes below because there's so many resonances in this structure. So it actually absorbs more light, and so particularly this curve is lower. And if you look at the slopes, then all of them are nearly 4 instead of 2. But especially these two, there's the highest and this is the highest, just around this percolation threshold. For just 11 nanometer, we are approaching 2 in the slope. So significant amount of samples, but they're still quite easy to make. And more white light generation. All this is of course, when we're looking to obtain this spectrum, we of course want as much light as possible. So we shine the laser, and it's femtosecond pulses. And it's quite high intensity, and it's focused. So we heat the sample a lot. There's a risk that at some point, of course, you will damage the sample. So, and we did that. So, of course, we made sure that when we have the measurements, we don't damage the sample. But we try to find the threshold where we have damage. For instance, here for 3 nanometer sample, this is 1.5, it's the power of milliwatts, it makes a damage. If we scan afterwards with a higher, lower power, we see that this high power gave a damage. This area actually gave some a little bit different effect. But if you look, for instance, let me see, for instance, if we look here, we see nearly no damage, and here is nearly no damage. We have all kinds of different effects actually, because if you damage, you can make it completely dark. You really kill this two-photon luminescence. So you practically burn away all these nice small gaps and small resonances in your structure with this power. And if you then investigate afterwards with this power, you see that you made damage here. And this was done for this polarization. But then if you move to this one, you see something else happened. It actually increased the signal. So it means the damage is not just the same in all directions, it's anisotropic. So it means it's different for this polarization compared to this polarization. And it's not so clear effect, and it's not so easy to see. There's many different effects here on glass. But if we move to silicon, then we have much more nice details, which I think is really worth looking into. And we did, of course. So we start writing lines with 3 milliwatts. We can make with this polarization lines here. And they are really, really, really dark here. If we make with the other polarization, we can write these lines. But actually, on the same structure, we made both this line and this line. And you only see these lines because they were made with this polarization. You only see these lines because they were made with this polarization. If you use the 45 degrees, something between the two, you see both lines. And exactly at the cross intersections here, you see they're completely dark. So we can really write with some power, and then of course when we read, we should be careful not to just destroy everything. So we have a difference of 3 here, and that's enough to distinguish between damage and no damage. And so this is how it looks, what I just showed. This is the white light generation actually is strong here. Here it's dark because we killed most of the resonances for this polarization. We killed those. In the usual reflection, we see, it depends how strong we damage, then we see some darker because we actually start to change the structure a little bit. If we do it really carefully, we can avoid having it seen in this fundamental harmonic. There's a balance because here we have this strong power dependence, nearly like 3 times, 4 times, depending on the intensity. So this is much more clear. It shows all the details, whereas this does not really show detail. If we have a small change, we will not see it that clear here. So that's this polarization dependence. The really interesting thing is we also can have a little bit wavelength dependence. So if we damage with this wavelength, it's nearly infrared. It's not really seen with the eyes, this wavelength. But if we damage with this wavelength, and then we start reading at other wavelengths. So here it's a little bit shorter. Here was where the damage was made. And here it's a longer wavelength than when damage was made. We see a nice detail that it actually is brighter for a shorter wavelength. And here it's dark, of course, we destroyed it. And here it's even darker. And this is in general, if we damage with short wavelengths, it just gets darker and darker and darker. If we damage with this, it gets either brighter or darker. And if we damage with the long wavelengths, it really gets bright here. And the explanation that, and we also have a lot of measurements confirming that, it is actually that the structure changes, of course. It actually starts melting. And it means if we have a lot of nice gaps here, or we have gaps with small particles, all these small nice places, they disappear. And that makes it dark, because the resonance disappears. But at the same time, the sphere well, here's the sphere. That's the ideal shape of a liquid drop. But here it's a little bit elliptical. So depending on the surface tension, when you melt the gold, and it is melted really locally, because it's only melted at the positions where the resonance is, then it becomes liquid, and then it has this spherical shape, and then it has kind of a resonance at a shorter wavelength. So a long particle will have resonance in general at longer wavelengths. A short particle will have resonance at shorter wavelengths. So we actually see the brighter. It's actually brighter at the shorter wavelengths because we melted it, and it became shorter. So it starts to have a resonance which it didn't have before. So, and I should say this we then map the really local near field. It's done with a atomic force microscope with this tip, and then you shine light on the tip, actually from below here, and then you see the scattering, and it means around locally 30 nanometer wide. We see these hotspots, and we see they depend really on polarization. For this polarization, we have a really nice hotspot here. It's here for 45, a little bit weaker actually, and here it's nearly gone. So it really depends on the polarization. So now we have proof that around 30 nanometer hotspots are local, a lot of different places inside the structure. Again, we should remember we illuminate, when we come with the laser, we illuminate everything. So we have just an average. And the same with wavelength, not that clear, but you see still, for instance, hotspot here, no hotspot here. So it is wavelength dependent. And what is then really going on, we try to make, now it's gold on silicon, so it's a little bit easier to make electron microscope images of that. So on this gold on silicon.
How big is the silicon?
The silicon, it's just it's a wafer, actually.
So
In this case, it's a wafer. It's a polished wafer.
Okay. So gold is basically evaporated on it. How do you prepare it? How do you prepare it? Do you evaporate it?
Yes, it's e-beam evaporated
Okay.
on the silicon. Actually, the previous images I showed, it was actually transmission electron microscopy images, and that was on silicon dioxide membranes. But because we have trouble with this charging, and this we really have a difficulty, but we don't have problems with charging on silicon. So it's a little bit easier to make.
So how thick is the gold layer?
Here the gold layer is, I'm sure it's around 5 nanometer here. So this percolation threshold where it starts becoming connected film is around, for silicon it's around 5 nanometer. And for gold on glass, it's actually 6 nanometer. So it's really, this also depends a little bit on substrate.
Okay, so you're almost making a film. Basically.
Yes, it's nearly around, I would say around 10 nanometer, then it's close to a film. Maybe 15 nanometer would be fine.
So basically there are a lot of gaps still.
There's still a lot of gaps, and there's actually also, it's still not a flat gold. You see all this, the last gold that will hit, it will of course still be some roughness.
But there won't be any critical dependence on this? I mean, whether or not you have gaps or not, or you get the gaps?
There will be, there is a really critical dependence, because if it's below 5 nanometer, it's larger gaps, and if exactly at 5 they start to grow together, and above that most of the gaps can be closed, then instead we have some nearly holes in the complete film. It depends a lot. And yes, and here's the non-damaged sample, this 5 nanometer sample. And then we damage it with 740 nanometer incident light. So remember again, it hits everything. The laser spot is much larger, it's around this size. But some positions are damaged, they are a little bit melted, some are not. So it shows that it's not everything destroyed, it's only a few places. And here again is most destroyed, he's most destroyed. So of course one of the last slides, we can use it for writing. And it was done in collaboration with DTU, so we decided to make SDU, DTU. So we write SDU with one polarization, and not at the same place we write DTU. And when we scan, depending on which scan polarization, then we have two different writings. And of course the resolution is not really impressive compared to, it's around 1 micrometer, so depends how many bits can you really write, how dense can you write. But we did try to make really narrow lines, so depending on how much power you use, how fast you move, and how large steps you move across the sample. For instance, here we moved this line, then we made this, and you see, then you make a cross section, and you see how long the signal goes down. And if you really want to write bits, you want, of course, below half to be sure that it's a bit. If it's 0 or 1, and then you really write it. So you can actually make writing. And the nice thing is that depending on how delicate you damage, if you do it carefully, you will not see it in the usual reflection. You will not see it with a normal microscope. Here you see it, but here you nearly don't see it. You nearly don't see it. But you will see it much more clear in the nonlinear image, in the white light generation image. So it can be kind of secret, maybe, writing. Yeah. So the last is this conclusion. I hope it fits nearly with the time. So first, this two-photoluminescence microscopy. It's a really nice technique to show the local field enhancement, and it can really reveal nice details. For instance, in this complicated structure, we can use the simple structure to have enhance the Raman signal, and we get all these nanometer hotspots for nearly all different wavelengths and polarizations. And we have super continuum white light generation, which is already a sign of extreme field enhancement. And we use this near field microscopy to really see directly these hotspots, which are around 30 nanometer. And then we used it for writing, and both actually we could do it polarization, mainly polarization, but also wavelengths. And you could imagine maybe you took several layers of this, and the only way you focus the laser, you will make the damage. In this layer you make damage, this one you don't make damage, because you really need a high intensity, and you need the short pulses. If you use the same average power but without the short pulses, then you cannot make this writing, because it really depends on the instantaneous really heating of this nanometer hotspot. Then it melts. Only the hotspot melts. The rest of the sample is actually quite cold because it's on silicon, and it removes away all the heat. So it's only the hotspot which is really this femtoseconds. It's melted, and then the resonance is gone, and then it doesn't heat up anymore. So after that it doesn't change. So it's interesting. So, and then acknowledgement. I should say special, I think, to Vladimir, because he made the near field measurements, and his name was not on before now. So, but he did this near field scanning, and then the funding, and then I would like to thank you for your attention. And then questions.
Yeah, thank you. I think it's a good summary of this research topic, and well, I hope there will be questions, so please ask.
Yes.
I'm always amazed at what you can do with material sciences at this level. I mean, taking macroscopic level things and joining them together in chemistry and so on is one thing. This microstructure, where the materials gain completely new properties, is fantastic. I was still worried about what's the relevance. You say more efficient.
Yes.
So efficient means, as I hear it, more signal to noise or more
Yes,
light out?
yes, more signal. So if we talk about the sensor, so the title was simple sensor, structure for simple sensor.
So can you, but the question is, can you make new things we couldn't do before? Because we could analyze molecules in many ways. So what is it that we are advancing here? It sounds like it's the cost or the ease of which people would use these sensors. Is it for academic use, or do you see it propagating to industries or everyday life?
It could be application, because of course this is well, basic research, but the application with perspective, it is the sensor, and it is to have it cheaper, because you can just have a large wafer evaporate on the entire wafer at once, instead of writing point by point with, for instance, with this really fine grooves. So it's really fast fabrication, and then it's relatively easy, and it's actually also a little bit, well, it's random, of course, the gold ends random, but on the average scale, then it's quite reproducible, because the average is, you have so many different hotspots that on average it's quite reproducible, and you can control the thickness quite well. So it's cheaper and easier and yeah, easier and faster, and maybe also a little bit more reproducible compared to some of other random things where you also make some self-assembly things. You can make some chemistry and also make some gold particles or silver particles. Here this is more reproducible, because they stop moving after you put them, and unless you damage it, they more or less stop moving. I mean, they sit there.
So it will be easier to produce, it will be less costly, it will provide better.
I think that would be the perspective on the sensor perspective, and it's, if you want to use such a substrate, it should be cheap, because you put some molecule on it, and then you don't want it to mix with the next molecule. So you want to throw it away after you're done, actually. But that's the sensor perspective. I think also I mean, well, this is of course, this is really just interesting. White light generation, and this writing, it could be like, actually for data storage, it's, there are some perspectives, and another thing is this white light generation, if you start combining it with all other plasmonics, maybe we have this, then we have the nonlinear, so it's nonlinear plasmonics, and it means we can get maybe some really nice things going on in this.
But it's still only for academia, right? Or
yeah, but still, plasmonics can be the kind of the next, well, it could be the next generation of electric circuits. So it's not electric, it's optical circuits in the computer, and again sensors, and so yeah, right now you can say it is academic. But
you even see an application in the writing part. I mean, we have many technologies for that.
Yes.
It looks great with the images you show, but it's not that small compared to.
No, it's of course here it's diffraction limited, but yeah, it depends what kind of resonance you. Probably will be difficult to make it much smaller, but yeah, it depends. Then on the other hand, it's nearly like hidden writing maybe.
And it's hidden not just because of the polarization, but because of the wavelength. You need to know what wavelength.
That's the next thing that you could say that actually has more dimensions, because you have, of course, you write the spot, but on the same place on top of that you can write for another polarization, and you will see both. If you use this polarization, you will see this picture. Like here, you see both pictures are actually stored on top of each other, and you could, if you have it depends what kind of laser maybe, but then you can write at one wavelength and another wavelength. You could also have two different pictures there. So already there you have maybe 5 different.
So you can make
3D
images
yes,
with the right glasses with different polarizations.
Yeah, that's probably, you're right, because if it's 3D you have 2 polarizations, and but then again you need a femtosecond laser to probe this white light continuum. So it's maybe there's of course a little bit gap from application to the research part.
So they're saying don't shine one of those in your eyes.
You
From
definitely
solutions.
not shine this in your eyes. It's first of all it's infrared, so you nearly don't see it, and the other one is the pulses. If you get it in your eye, you will get tiny spots around where it hits. So it's not so. Definitely not. It's with glasses. Yeah. Oh, sorry.
How big was the enhancement from the, from just the, for example, 5 nanometer gold film from the, not gold film at all?
Yeah.
If you
It's
just do spectroscopy on the sample without the gold film, how big was the enhancement from that?
It's a really good question because it's still only an estimate. It depends really how small we think this spot size is. I mean, the signal is only coming from this spot. Is it then only coming from the it's coming, the luminescence is coming from the gold. So it depends what kind of volume compared to if it was a flat. Yeah. And so it's really an estimate, but we have around an estimate around 6,000 times. So it's. And it's so yeah. So come on, it is 3 orders of nearly 4 orders of magnitude.
Okay.
So it's it is significant enhancement.
Okay, that's it.
But again, it depends really how you estimated it. But it's definitely an extreme enhancement.
Okay.
It's just depending how you really compare this. So there is a good perspective. So. Yes.
Do you then just put the sample on the gold plate, or what do you do with the?
Yeah. So yes. So we have the structure with the thin structure, and that you mean the kind of molecule we want to detect.
Yeah, for example.
It can be done in different ways, but here, well, in our lab we just you can actually just put a small drop of this,
Okay.
or you can also put it down into the substrate, take it up, and then remove as much as possible. But the idea is that this molecule that you want to detect is quite important. That should start to stick close to the gap. It should sit maybe preferably in the gap. And depends how serious your experiment is, because you can treat the gold with some groups that really bond to the gold, and then afterward would bond to these molecules that you want to detect. Then you could get them to sit exactly in the gaps. But it's of course I think this structure is not so difficult, because if you put a liquid on this, it's so thin, this structure, that it will probably reach the gap. But here, this grooves, they are nearly they're around what? Well, okay, they're nearly 1,000 nanometer deep, a little bit more actually. And there you can imagine it's difficult, maybe because of surface tension, that the water or something else will not reach the bottom, and the enhancement was in the bottom. Here it will reach the gap. It will at least be only 3 nanometer away from the gap. And the field will spread a little bit. Yeah. This is, yeah. Yes.
How much is theoretically understood? Before
sorry?
you do the actual experiment, how much is theoretically understood? I mean,
Uh,
the size of the sample and so forth. I mean, can you actually, in principle, predict the level of conductivity you're going to get to the level of the electric field?
It's well, for this one you can predict it quite precise with simulation. Here I would say it's difficult, because it's well, you can make something that looks a little bit like this structure, but here it's a little bit easier because it's periodic. Fine, you can extend it. Maybe not this, but at least some part of the structure you can extend it, but and only simulating in 2 dimensions maybe. But here it's different in all directions. It's a little bit more difficult to well, you can make some simulation, but it depends how precise it will be.
So compare, for example, to graphene, right? So where all this fantastic property of graphene has been found. I mean, can you make a gold version of graphene? Or
that's. I'm not sure. Well, you could at least put a layer of one monolayer of graphene something below. I'm not sure if it would help something. Maybe, but that's again it's interesting to do.
I think what we're challenging here is perhaps your definition of simple in your title.
Yeah, that
When you
is
say
true.
simple, it's really the process that's simple,
The
because your
process.
structure is not simple at all. It's actually very involved. Simplicity to me is like crystalline, simple unit repeated by a symmetry. You don't have that, and that's why you cannot.
Yes.
Calculate. So what we're asking here is, can you guide the assembly process instead of just controlling the coverage? I'm not an expert. Can you use catalysts, electromagnetic fields, whatever, to try to guide the assembly so that you could, in fact, make more regular structures? Would
Yeah,
that be the potential for that?
That's probably a task also of at least you should simulate, or then it's kind of a chemist, because if it will, the gold will land here, and depending on the surface tension and actually the pressure in this chamber and the temperature of the substrate and the speed you evaporate, I mean, if it's fast or slow, you can actually change how well it distributes, and if it's large particles landing at once, or if it really starts growing. And maybe if you modify the substrate with some pattern, maybe then the gold would seek to some of those places, and then you could. But that's kind of speculation, maybe. But I think it's possible. It's just you just need the knowledge about how to modify this, maybe surface tension also. At least it could be.
I mean,
It's true. It's not simple. From that perspective, not simple.
If you could use other materials that could be allowed to diffuse around on the surface before you tie them down, you might get different, another parameter to control.
Yes, but that is
Just
true.
ideas.
If you but it's true if you I mean there are some chemistry that really likes to bound to gold, and if you actually here there's nothing, there's only glass and then gold, but if you put some additional monolayer or maybe not monolayer, maybe something else that you could have in a nice pattern, and maybe graphene, maybe. I don't know. So
Maybe.
yeah, of course, because then if you had one monolayer and it has a really well-defined structure, this graphene, this hexagonal structure, and then maybe then but maybe. Yes.
So maybe picking up one of Mikael's points, and as a non-physicist, a really ignorant question. So the mechanisms that were at work seem very different in the complex and simple versions. And also, so my question is, so the like the percolation, the hotspots, and so on.
Yes.
They don't play a role in the complex structures at all. Or
In this structure, you mean the percolation does not play a role, because this is kind of more or less solid gold, but it's at least maybe 1 micrometer thick gold layer. But then, of course, there's still some roughness which will play a role, and but still, it's more the shape. Here for this one, it's a groove, actually triangular groove, and there will be actually, depending on the depth of this groove, there will be a resonance, because the light will come from from the top of the groove to the bottom, and this distance there will be a wave propagating, and then a little bit of this, and this is a wave in the electrons in the metal, and it will propagate to the bottom, and if it reaches at a certain point at the same instance the top again, there will be a resonance. So there is the resonance because of the geometry. Well, you can say this is also a resonance because of the geometry, but it's really it's more localized to each individual particle. Here it's more propagating. Here it's actually propagating electromagnetic. It's called surface plasmas. in its oscillations in the electrons propagating on the gold film. And here nothing really propagates because there's only some connections. There's more interactions between individual gold particles. Yeah, I think it's
Because it looked like it's very different things going on. They're very different mechanisms that produce, these effects.
Yes, well, you can say that the first slide, but I'm afraid to go back for the first slide. But you either had the localized, very localized to the particle resonance. Well, let's go back. But just the problem is that I experienced some delays here. So yeah, let's see. So the first slide, you either have it localized to a particle, or you have it propagating. Yeah, let's see. Yeah. So either it can propagate along the surface, or it can be localized to. This is an isolated particle. So this was actually the playing the main role in this grooves, and here this is mostly this one. Of course, if it starts to be connected, you can have both these propagating along this connection, and then in the small holes left in this not complete gold film, you will have this kind of, actually the opposite, because the hole can have the opposite of a particle. You will still have this kind of resonance. Yeah, so that's the, it's, yeah, I think it's interesting. So,
maybe I can add to this that the difference is that when you have this near percolation threshold, this random structure, it's very similar to this so-called fractal structures. So the point is that there are all sizes of particles, all gravity-between particles, and all shapes obtained automatically by the nature of the deposition. And therefore, there is a field enhancement for all wavelengths. They might be sitting in different places. These places, they're dictated by the local geometry, but also the non-local, the global environment. So everything plays a role. And from the point of view of these substrates for source, that is really like a cheap and easy solution that can be, I don't know, we are not thinking about commercialization, but in principle this can be a way to do, because there are several companies that are producing so-called source substrates. But in the field enhancements that they promise is quite large, actually you can get, but this is only if you're using particular, for example, pump laser. And you also have to be careful with the polarization and maybe even with the angle of illumination or detection. You see? And then, of course, you would like to have it disposal and throw it away anytime after you put something, analyze, and you throw it away. This is also not an option because they're quite expensive. So here, this is we get all effects, and if you show again the cell spectrum, you
yes,
really have quite a large difference. Yeah, you see here when you come to near percolation, they become really very much pronounced, and actually the one which is close to the flat gold surface.
yes, this is the black. Yeah.
This is still that you see something. It's only because this is not really flat. It's 12 nanometers. If it's a just flat substrate, at this intensity of incident light, nothing would be seen. You have to go to the larger signals. So that is really what can be promised as an applicational side. From the scientific side, of course, just to describe this percolation threshold in a little bit better way than saying that you have everything. You can imagine the that would be nice, but it's difficult. People have been tackling these issues for the last at least 20 years, depending on the level of instrumentation and the computer programs, meaning that computer time and speed available and the memory. It's like going in waves. The first wave was around the 80s when the source was discovered, and around 90s when near-field microscopy appeared. And now it's starting to be coming again because of the possibilities to use it for the quantum technologies also. It's really